Hi there, I'm Zefyr Scott with HKN at UCLA. Today we're going to look at how to do vector and matrix operations using three different tools: Matlab, Python, and Excel, or you can also use Google Sheets. Why learn all three? Well, each of these tools has some pros and cons. Matlab stands for Matrix Laboratory. It's an interpreted language explicitly designed for efficient matrix calculations. It's quick and easy to work with, but it's proprietary and closed source. So if you're a student, check to see if your school offers a license for free. If it doesn't, there's student rates, so you can get the products more cheaply. And if you're not a student, it costs a bit more. Python is an interpreted language. It's free, open source, and again, it's very easy to work with, but it doesn't handle vector or matrix operations natively. However, its Numpy library offers these operations, and its performance is generally comparable to Matlab. Excel is not an interpreted language. It's a powerful spreadsheet program which can perform vector and matrix operations as well, and sometimes I find it's a better option than using Python or Matlab. It's part of the Microsoft Office package, which is closed source and proprietary. Note that Google Sheets is a great free and open source alternative, and everything we're doing in Excel today will also work in Google Sheets. I generally find that Excel works a bit better for some things, and it's free for students, so I'm using it for this video, but you can use whatever you prefer. We're going to start with Matlab. So with Matlab, let's look at how you can go ahead and make a vector. You can make a vector where each element is named individually. So a row vector, for example, we're going to go ahead and call it row. And we're going to make it a row vector by separating the terms using a space. And when I run that script, I'm going to put these into a script here so you can kind of see these historically of what I'm doing. I wind up getting in the workspace a row vector. It's row because I called it row. That's not telling you that it's a row vector. It's just telling you the name of the variable. But I can see that it shows 4, 2, 3. And in the command window, if I want to display that, I can see that it's definitely a row vector. In the same vein, if I want a column vector, I'll go ahead and put that in as column, and I'll separate my values with semicolons. And then you can see here in the workspace, it's going to list, again, separated by semicolons now. And if I type call for the name of my vector, it shows it as a column. So that's exactly what I want. And you can go ahead and get their size. For example, if I'm going to get the size of the row, it's going to, I'm going to type size. I'm going to put this as size row so that it'll show up in the workspace. And I can see that the size of my row vector is 1 row by 3 columns, which is what I expect. And if I want to get the size of the column, just to, again, demonstrate my rows versus columns difference, I can see the size of my column vector is 3 rows by 1 column. Now you can also generate a vector as a sequence of values separated by regular intervals. So for example, if I'm going to do a standard increment, let's go ahead and call this, I don't know, A1, just for values that I'm not going to be using later, but so that they're clearly separated. I can see that this counts up from 1 to 10, my start value to my end value, with a single integer spacing value. If I want to have a skip value, or if I want to do anything kind of funky, let's go ahead and call this A2. For example, if I want to skip by 2, this will count up 1, 3, 5, 7, 9, and then of course there's no 10 value because that would be a counting up by 1, and so it just leaves off any values that it's not going to use. And I can go ahead and do that with float or decimal values as well. It doesn't have to just be integers. And if I want to count backwards, I just have to set my skip value to be negative. So as an example, I'm doing the same exact thing as A1, counting up from 1 to 10, but now I'm counting down from 10 down to 1 by a skip value of negative 1. And there you go, 10, 9, 8, and so on. You can also make vectors as a series of zeros or ones. So for example, a row vector of zeros. This is a row vector of 1 row by 5 columns. And I can see there's my vector separated by commas of 5 zeros. And a ones vector, which will also be useful for sometimes. Let's go ahead and make this a column vector. So this is 5 rows by 1 column. And there you go. It's separated by the semicolons, so it's 5 rows by 1 column. And you can imagine, generally when you're doing vector operations, sometimes you want to add a single add a single value or multiply by a single value or things like that. So it can be useful to have a row of ones, and you can modify that by multiplying it in some way, or a row of zeros where you want to work with that in some way. So useful tools. Now you can get a transpose of something. So for example, if I want to go ahead and get my row transpose, oops, an extra equal sign, that's not necessary. You can see that now it's taken my row and it's made it a row transpose. It's put in these semicolons, and I can sure enough verify here that if I went ahead and typed that out, there you go. Row transpose is a column exactly like you want. Now there's another way that you can do this. I'm going to go ahead and show this as row T2 with my awesome, not the most useful for long-term programming, but fine for demonstrating here, variable names. You can also use the transpose keyword, or excuse me, the transpose function, which will do exactly the same thing. You can see it looks exactly the same, so it doesn't really matter which one you use. You can also do some common vector operations. So for example, for the dot product, let's go ahead and do this as D. Now I am dotting row and column, and if you've done any sort of vector operations, you know that generally when you multiply a row vector by a column vector, which have the same number of elements each, that's going to be the definition of your dot product. That's just how you perform the dot product. And so it happens to be that the way I'm typing it in is going to give us that value, which if you go ahead and do the math, you'll see that the dot product is exactly what I'm getting here. It's 28. But it doesn't actually matter what the shape of these two vectors, or I should say what the direction of these two vectors is. You can go ahead and do that in either order, and Matlab will do the heavy lifting for you. You'll see that this is still 28 even after running that script again. Same thing with getting a cross product. And unsurprisingly, this is just called cross. And if you do a cross product by hand, you'll see that the cross product you get should be exactly this value that we're getting right over here. Now, you can also use multiplication for a dot product. Again, what we said before with the dot product, it's defined as when you multiply a row column by, or excuse me, a row vector by a column vector. And so, for example, if you go ahead and do 2, go ahead and say that is row times column. I had almost all these typed up beforehand to copy and paste, but not all. And you can see that here, D2 gives us our same exact value. Now, for a comparison, notice that if we do instead our dot product as row by row, and we try to do, we're not going to do this part yet. We notice that row dotted with row is going to be 29. If I do row dotted with row, row times row, I'm going to get something a little bit different. It's going to give me an error because it's not actually, it says something about here about element-wise multiplication, and we're going to look at that in just a moment. But here, if we're just multiplying two vectors, that's not, a defined vector operation. They have to be in the, when they're both in the same, these are both 1 row by 3 columns times 1 row by 3 columns. That's not defined. And so what we have to do is go ahead and transpose one of these. So row times row transpose. And if you do the math, or if you're familiar with vectors, you should know that that is here, that's just how we would go ahead and dot product those two row vectors. And sure enough, or that same row vector with itself, and sure enough, we get the correct result. Now, notice that it said about element-wise multiplication. Let's go ahead and take a look at that. If we have vectors or even matrices, but we're not covering matrices in this particular video, if we have vectors with the same dimensions, we can operate element-wise. So we were talking about multiplying row with itself. Let's go ahead and call this element-wise, E for element-wise. If we just say row times row, oops, and if we listen to exactly the thing I was saying, if we, again, putting in just the asterisk to multiply, that doesn't work. But if we put in the period before an asterisk, that will actually give us our value. And if we take a look at what E is, again, this is row times row, well, what was what are our row vectors? We have 4, 2, 3, and E is 16, 4, 9. And sure enough, that's 4 times 4 is 16. 2 times 2 is 4. 3 times 3 is 9. This is operating element-wise, and that's exactly what we want. And again, just kind of keeping track of things. If we were to do row dot period times row asterisk, just for making sure you have a sense of what will happen with these things, you will go ahead and get a result, but look at how this is now actually 3 rows by 3 columns. You can see 1, 2 semicolons indicating this is, as you can see if I hover over it, it's a 3 by 3 double. It's a 3 by 3 matrix. So what we did here actually was we element-wise multiplied a row vector by a transposed row vector, by a column vector, where each one had 3 elements. And so that actually gave us a matrix. Keep in mind that if you, functionally that's gonna do a little bit of a different behavior. So just make sure that you keep track of what exactly you're doing when you're trying to operate element-wise versus if you're not trying to operate element-wise. Now, again, this is just showing how to multiply element-wise. Well, how do you do other element-wise operations? If it's something that uses, again, just some of these standard arithmetic, standard arithmetic operators, you can even for like a square root, for example, I'm going to just call this E2 because it's going to give us our same exact value. If I type row dot up caret, if you've ever done any programming, you know that in general, if you want to get 2 squared, you'll type 2 to the 2 power. Well, we're going to do row to the 2 power using our dot operator, and that's going to give us our same exact value when we get E2. So perfect. Same thing again for division. You don't need to do this when adding. If you're just trying to call this adding, and you want to do row plus row, you don't need to add the dot or the period operator. That's just going to work directly, and that will already be element-wise because addition of vectors is already defined that way. So this is just for when the definition doesn't already cover element-wise operations. So also notice that we don't have to do this dot operator behavior when working with scalars. This is expected for multiplication and with division, since scalar multiplication, the dot operator, as I said, is expected for multiplication with division, since scalar multiplication with a vector is defined. I said that kind of weird, sorry. When we're multiplying 2 vectors, we're expecting that we're going to have to go ahead and use this period operator because for vector multiplication, element-wise multiplication isn't the standard. If we're multiplying by a scalar, so we'll go ahead and call this m, and we're going to say we want to multiply row times 2. Again, I'll go ahead and do times 3 to clearly disambiguate between the power there. But yeah, if I'm multiplying my row by 3, that's pretty standard, and of course, when you're multiplying a vector by a scalar, this looks like pretty standard behavior. We get our 4 times 3 is 12, 2 times 3 is 6, 3 times 3 is 9. There we go. What may surprise you, though, as another adding, we'll call this adding 2, or adding alt maybe, because I want to make clear that this is going to definitely get a different behavior than the row plus row that we did before. If I do row plus 3, now usually we would expect that we would need to maybe do row plus 3 times 1's 1, 3. And this will work just fine. I'll go ahead and show you. So here we added a row of our original row vector plus 3, 3, 3. And sure enough, here our adding alt is 4 plus 3 is 7, 2 plus 3 is 5, 3 plus 3 is 6, and that's great. But we can also do this a slightly easier way, where Matlab, again, just kind of does the work for you. And we're not even going to need to add the 1s. It will automatically take that 3 scalar and turn it into a vector of 3's. And there you go. You can see that it got you exactly the same value. So again, there's a lot of cool things that Matlab does behind the scenes that's very, very powerful. So finally, to get values out of these vectors, we're going to use indexing. Notice that Matlab starts array indexing at 1 and uses parentheses. So for example, I'm just going to go ahead and type this into this window here. If I want to get the first value from row, that's going to be row 1. And sure enough, the first value from our row vector is 4. That's what we expected. And if we want to get the second value from our column, if only you could see how badly I'm typing here. There we go. You can see second from col is now out of screen. That's 1. And sure enough, our column vector was 5, 1, 2. So there's our second value. So let's go ahead and look at an example of using all this put together. I'm going to go ahead and clear this stuff here because it's no longer necessary. I'm going to clear out the workspace just for clarity. If you ever want to, what you just saw there, I typed clear to clear out my workspace. I can also type CLC to clear the command window. And that's just convenient. So let's say you're doing some lab, in like your introductory physics lab to verify Ohm's law. You know that voltage equals resistance times current. That is voltage equals resistance times V equals IR. I guess I typed those in a manner that is backwards, so I'll go ahead and do it this way. Oops. There we go. Now I look like I know the order of these values here. You've probably seen this equation before. It's Ohm's law. And so let's say you have a mystery resistor with the bands all worn off. So you're applying a range of currents from 10 to 100 milliamps. Oop, looks like I changed the values here. This is actually going to be 1 to 10 milliamps. It's just super small values. So we have some vector like that for our current. It's 1 to 10 milliamps. And there's our current vector. And you can see that when it's small values, it'll actually go ahead and maybe do like some multipliers. This is 1 times 10 to the minus 3, or 1 times e minus 3. So you can see some of these things sometimes. So then you can enter your measurements. Say we went ahead and manually went through with our DMM, and we calculated these voltages that I generated by slightly random number typing earlier on. And so you get this vector of voltages, and that's great. These are useful. So we know that from Ohm's law that voltage divided by current is the resistance. So let's go ahead and enter that as resistance equals voltage divided by current. And that gives us this resistance vector. And we can see, just from looking at it, this is a whole bunch of values of 1.2 something something times e to the 3, or about 1200. There's about 1201. There's about 1201. There's about 1199. You have this range of values that's all pretty close. And that pretty much is what we expect based on this. You can eyeball from the numbers or go ahead and do the math by hand if you want to do that. You can see that what we're getting here is about a 1.2K resistor, 1,200 ohm resistor. And we can plot what we did here. So in a video that we will hopefully do in the future, we'll go more into how to plot stuff, but here's a really, really basic plot. And hopefully it'll show up in this screen. If not, I'll move it over. Nope, it did not show up in the screen. Awesome. So this is a plot that has no title, no labels. That stuff, again, we'll go over hopefully in another video. But what you can see here is on this, the first axis here, this x-axis, is our first value of the current. And this is counting up from 1 to 10 times 10 to the minus 3. And again, you have to keep an eye on your values. And then your y-axis here is the voltage. And that's counting up from 0 all the way up to 14. And you'll find that this slope then is going to be your 1200 ohm slope. And so that's super useful. And you can even do things like, for what we just looked at, maybe you don't actually, you want your current in milliohms instead. So you can just go ahead and divide that by 1,000. Hopefully I did my math right there. Otherwise this is going to be embarrassing. Oh, I did do my math wrong. That should be times 1,000. Ha ha ha. And there we go. Now it's now it's in millions because I forgot numbers. Great. So that's an introduction to how you can go ahead and do some rough calculations in Matlab. And you can imagine that obviously for purposes of a quick lab, obviously this was kind of, you know, typing out all those numbers might wind up being a lot of work. It kind of depends on how you want to do it. And it depends a lot on also what kind of lab you're working on or what kind of work you're working on. If you're working with something where you have a very, very large number of values, this becomes very, very powerful. For smaller numbers of values, it's very easy to use, but it might be kind of annoying typing it out. So next, let's go ahead and take a look at Python. So Python has a data type called a list, which looks a lot like a vector that we were just doing in Matlab, but it doesn't quite work like one. So let's look at an example. We had our row vector from before. Now notice that we don't need to type the semicolon at the end, but it'll show up right here in our variable explorer for the particular IDE that I'm using, which is nice and convenient. And it says it's a list. Now notice that if I do this row times 2, this is an operation that if we were working in Matlab, this would make sense. We're just taking, or excuse me, if we were working with a row vector in Matlab, we would expect this to just double our vector. Excuse me, double the values, but you can see it actually doubled the list. So that's not useful at all. We don't want to do that. What we want in Python is we want to use Numpy. So what we're going to do is import Numpy. And you'll commonly see people calling it, saying, or they'll write out import Numpy as NP. And this is this is called aliasing. It allows you to go ahead and instead of every time you want to call a Numpy function, you can just call it NP instead of Numpy. So it's a little bit less typing, and we'll do that. So once we have that imported, we can then go ahead and write some arrays, or excuse me, write some vectors. The first thing we're going to look at actually is what's called a Numpy array. So this is a single dimensional Numpy array. I'm going to have to probably type these all out. I'm going to not type. If you imported Numpy as NP, then instead of typing out Numpy entirely, you can just type out NP, and that's nice and simple, but I typed out all my examples using Numpy as a full word, so I'm not going to alias it. Anyway, so this is a Numpy array. It's single dimensional. Now, a row vector is a two-dimensional vector. It's 1 row by 3 columns. A column vector is a two-dimensional vector. It's 3 rows by 1 column. A Numpy array is a one-dimensional vector with 3 elements. You see that it's an array with size 3, comma, nothing. And so this is going to become important because of some of where Numpy is very powerful. We're going to start by doing some, we're going to start by actually working with Numpy arrays in a format that makes them look like vectors and columns, and they can be used in that fashion. But when we're going to move on to some of the examples that are comparable to what we did in Matlab, we're actually going to wind up working with Numpy arrays because they're very dynamic and useful. Now, that doesn't mean that working with something in a row or column format isn't going to be useful. It just means you'll have to keep track of what the dimensions are of the object that you're working with and think about what you're trying to do with them. So let's go ahead and compare what we just wrote, this Numpy array, to a Numpy row vector. This is the same exact values, but notice that instead of being comma separated with 1 set of square brackets, this actually has 2 sets of square brackets. And you can see then when I type this into, it's going to clear out my old row, this has, again, this is familiar, our size of 1 row by 3 columns. Again, the value looks very similar to the array, but it's a little bit different. It's got these 2 brackets. And the bracketing maybe looks a little bit funky. Hopefully the column vector will help to clarify it. There's a column vector. Now each row is in one set of square brackets separated by a column indicating a new row. And sure enough, again, our size is now 3 rows by 1 column. And it shows a little bit weirdly in the value here. You can see just the first 2 rows displayed. So to convert between these dimensions, you can reshape. And this is one of the very powerful things with Numpy. So if you reshape with 2 numbers, as an example, when we're going to, I'm just going to put this right here. We'll call this r_reshape. It's going to be r.reshape 1, 3. And so what we're doing here is we're taking this 3-element, one-dimensional Numpy array, and we're going to reshape it into a 2-dimensional, still 3-element, Numpy row vector. And there you go. Now you can see that our reshaped array looks exactly like our row vector. You can also go ahead and reshape a row vector into a Numpy array. So go ahead and call this row reshape. And you can see I'm using the same idea, but this time I'm taking my row vector, my 2-dimensional row, and I'm just passing one value here. And since it's just one value, it's one dimension, that's going to give us something good. Now, what we do want to be mindful of, again, is how many elements we have. If we try and reshape to 2, well, again, we have one value here, it's 2-dimensional, but we're asking to reshape this 3-element object into a 2-element object. And so it gives an error, unsurprisingly. So don't do that. Now, you can also use this for transposing, as you can imagine. And to kind of get a sense of, remember that our Numpy array here, this is a one-dimensional Numpy array. It isn't strictly a row or a column. So we reshaped that previously to be a row, but we can also go ahead and reshape that to be a column by saying, make this have 3 rows and one column. Same idea, and you can see now it's basically transposed, but it's not true transposed. Originally, it was neither a row nor a column. It wasn't. It didn't have the specific shape that we're talking about for either a row or a column, and so we were able to go ahead and say reshape this one-dimensional object to a 2-dimensional object. Try making it a row. Try making it a column. Depends on what exactly we pass in. Now you can also go ahead and get the size, just like we did before, except that we're going to call it the shape now. So our row shape is going to be row.shape. And you can see that it is this object type called a tuple, and that has 1 row and 3 columns, which is what we expect. Now you can still generate a vector as a sequence of values separated by regular intervals. So I don't remember what we called this before. I think we called this D, D1 or something like that. And we use the arange function. And you can see that when we do this arange function, now we see that Numpy is actually numbering in an array. It actually numbers from 0. And so remember when we typed in for Matlab, we wanted to get, oh, that's not saved, haha. Well, when we typed for Matlab, we wanted to get a row that was from 1 to 10. We started at 1 and counted up to 10. Here, when we have Numpy arange 10, we're getting from 0, because that's a starting value, up to 9, because it does not include, when you're using the range functions, it doesn't include the last value. Now, notice that if we wanted to start at 1, we can. We just have to specify that. If we don't specify the starting values, then it's going to go ahead and just assume the starting value is 0. And so again, in this case, it just counts from 1, which is our starting value, up to 10. Excuse me, up to 10, but not inclusive. And we, again, have the ability to skip. Oops. Very bad copy and paste job on my other screen, which caused problems, which was entertaining. And so to skip, whereas before with Matlab we typed 1 to 10 with the skip value separating, here with the Numpy arange function, we're typing 1, 10, 2. And again, that's going to count 1, 3, 5, 7, 9, and so on. And again, same idea. We can go ahead and use that last parameter there, the skip value, backwards. Same exact idea. And you can see that this goes D4, goes 10, 9, 8, 7, and it goes down to 2, but doesn't include the last value. Same thing, you can also make vectors as a series of 0s or 1s. And you'll notice something really interesting here is that we're using double parentheses because there's only one parameter we're passing into the numpy.zeros function, which is the shape of what we're trying to make. And so you can see here our Z array is an array of 0s. Notice that it is made as an array of 0s as floats rather than integers. So if you're working with something where it matters that something is a decimal or a not decimal, keep track of that. And same idea, you can do that to get ones. Here we'll make a column of ones. This is 5 ones, and here's our array of 5 rows by 1 column, and you can see the first 2 rows there, each are rows of a single value, just a 1. And again, we have the ability to get transposes. We already saw that we can get a transpose by using the reshape function, but you can also just use the t parameter. I'll go ahead and do this right over here so it's very clear. I'm going to call this RT. I'm going to call it, I'm going to call this RT because this is just transposing and it should give us the same sort of value. That kind of weirdly. Remember that r_t, that's my variable name, but r_row.t is how I'm going to go ahead and make this transpose of the row. And I can see that sure enough, row_t is my variable, but that's the transpose of my row vector. So nice and simple. And notice that here, row_r, remember that's my reshape that takes my row vector and turns it into a single dimensional Numpy array. So just again, keeping track of your types. And then we've got, again, some common vector operations. Notice that the dot product here, we're going to take a look at that. We'll call that dot. There we go. And dot, that's going to give us that same 28 that we had before. Notice that this outputs an array value with a single scalar element rather than outputting a scalar directly like Matlab did. So you'll have to extract that. And we can also get a cross product. We'll go ahead and call that cross. And so notice that this can take single dimensional arrays or rows, but not columns. So, and you'll have to reshape if you try to pass in a column. So here I'm taking this row, and I'm taking this column, and so that'll work, but you'll have to get some bad, or you'll get some bad values if you try to do just row column directly. It says incompatible dimensions. Now notice that if I do the same thing with the dot product, that works fine. So it's able to do some reshaping, but with the cross product, it has some specific requirements. Whenever I'm doing dot and cross products, I'm usually working just with a Numpy array directly. That usually is what you want. And again, you can use multiplication for the dot product. You have to use a kind of funky operator that honestly I hadn't actually used until I did this tutorial. But you can use the @ operator. So we'll go ahead and call this .2. And this is row @call. That's going to be the definition for your dot product. And again, you can see that gives the same exact value. Again, it's not something that I've ever used. I always just am using the, I'm not even using the, excuse me, I'm always just using the numpy.dot product. It's very commonly used, and I just use that with Numpy arrays usually. Or single vector, excuse me, single dimension Numpy arrays. So remember that with Matlab, to make it an operator work element-wise, we just added a period before it. With Numpy, there's often a dedicated function, which is a little bit funky. So for example, to take the power. Now, excuse me, not to take the power, to do multiplication, we literally just use the multiplier. So for multiplying, we just want to do element-wise row times row. We just type it exactly like that. And you can see mult, again, this was 4 times 4, 2 times 2, and 3 times 3. And that works great. Now, notice that when multiplying a one-dimensional array with a two-dimensional array, the one-dimensional array will get what's called broadcast to the two-dimensional value as long as it has the same number of elements. So for example, remember that our array here has 3 terms. Our column, this will be our row, also has 3 terms, but these are different dimensions, and that's actually going to be okay. We're going to go ahead and take 2, which is going to be array times row. And notice that, again, our array value has the same exact values as our row value does, so we expect mult2 to wind up being the same number that we got from mult. And sure enough, that's, oops, That's what we get. We get the same vector out of it. Notice that it's even two-dimensional. So what's happening with broadcasting, looks like yeah. So what's happening with broadcasting is that I'm going to type this over here. Our row vector here has a shape, as we can see. Where did it go? Our row vector has a shape of 1, 3. Just type this. I'm not going to compile this. I'm going to run the script, I should say. Our row shape is 1, 3. And our array shape is just 3. And the comma is because it's basically to show that it's a tuple, which is a data type. And if you get more into Python, you'll know more about what that is. But that's beyond the reasons why it's written that way are basically because the data type needs it. And you can learn more about that in hopefully another video. So broadcasting says, okay, these two dimensions don't match up. Let's just add 1s to the left of our shape until they do. So you add a 1 there, and now the shapes match. And so now you can go ahead and operate on them together. Now let's say, hypothetically, let's say that the shapes did not match. Maybe this array, I shouldn't say didn't match. Let's say hypothetically they were unmatchable. This was maybe a shape of 4, and so you go ahead and add the 1 there. But now they have the same dimensions, but clearly they don't have the same shape. And so the operation just isn't going to work. So that's the idea behind broadcasting. It allows Numpy to do very dynamic reshaping of objects, and that's part of the power of the one-dimensional Numpy array. If you get into any sort of machine learning, this becomes critical because you're going to be constantly reshaping gigantic matrices of a whole lot of values, where sometimes you need them to be 3-dimensional, and sometimes you need them to be 4-dimensional, and so on and so forth. So broadcasting, very powerful. Now, remember that with Matlab, to make an operator work element-wise, we just added a period before it. With Numpy, there's often a dedicated function. I think I was starting to say this earlier. So as an example, we're going to take the power. With arithmetic operations, we didn't need to do this. With anything beyond arithmetic, yeah, usually we need to do something else. So with our Numpy power, we'll go ahead and call this power. And this is just taking the row vector to the second power. Oh. I think pow might be a reserved term, so this may or may not work. All right, I'm gonna just call that P. I think it's gonna give me the same thing. There we go. So notice that it gave you this kind of funky value, but when we go ahead and type it out or enter it, it actually gives us our desired array. Just for comparison of what the output looks like, again, that was this value here. If we compare it to a row, the difference between these is just whether it's explicitly stating the data type along with it. It's a specific object rather than the value. And again, kind of beyond the scope of this video, but it gives you something that you can still work with in a similar fashion. Don't worry about memorizing all of these different functions like power. You'll find like a bunch of different things. This square root, I think, is one of them. Whenever you're trying to find them, you can just go to your browser and search for the operation. So what you would want to do is type in something like, I thought I had an example. Yeah, you can type in something like Numpy elementwise power. So for example, go to Google and you type in Numpy elementwise power. You can type in elementwise without a space or with a space. Any of those should be fine. And the key here is you want to type in Numpy, which is the library name, and then power, which is the mathematical function you're trying to do. Maybe you want max, maybe you want square root. Just type the actual name of what you would call it if you were in a math class, and that's going to get you the best results. Now, when you're looking at the results that you get using Google, your best results are going to be anything that's coming in from numpy.org. That's going to be the Numpy official documentation, and that's going to be your best resource for the strict definition of the function and examples of how to use it. That's what Numpy wants people to learn from. I like Geeks for Geeks as well. Geeks for Geeks. They have really good examples when, especially sometimes, the Numpy documentation isn't always going to be the clearest. And so Geeks for Geeks spells things out in a way that's really clear. You'll often see examples from Stack Overflow. Obviously, not all of these are URLs, some of these are just text. Stack Overflow is a great resource when you have questions, but that means that any page that you go to on Stack Overflow is going to contain a question that someone expressed, which may or may not be clear and may or may not match the question you're trying to ask. And then answers, which are generated by whoever was bored or interested in showing how much they know about the world and typed up an answer. The answers may not be clear, they may not be relevant, and they may, in particular, they're often not relevant for the level that the user is asking for when they're asking a question. So I generally recommend, if you're going to go to, if you're trying to find how to do a thing in any programming language, Python absolutely included, you start by searching for the programming language or the library you're using, whichever it is, followed by just a word for what you're looking for, again, such as power or max or whatever it is. And then look for any official documentation, or again, something like Geeks for Geeks that is a basic tutorial, and only look at Stack Overflow when you try those things and then it doesn't work. Usually when you have, that's gonna be helpful when you have a more complicated situation that you're trying to deal with, and maybe someone has dealt with that situation before. Anyway, back to the tutorial. So finally, to get values out of these vectors, again, we're going to use indexing. Now, we mentioned before that where Matlab starts its indexing at 1, Python starts its indexing at 0. So for example, to get the first value from our array, our array first is going to be R0. And there you go. The first value in our array is a 4. If we want to get something out of the row or the column vector, remember those are 2-dimensional values, so we actually have to index twice. So for example, the first value in our row vector, oops. Ooh, I cannot type. We'll just pretend we never saw that. First value on our row vector, there we go. So a row, and again, we got a 4, but we have to say first off in the first row, and then in the first column of the first row, again, using 0 as our starting value rather than 1. So to kind of show this a little bit deeper, for example, if we're trying to get the second value of our column vector, we would do column 1, so the second row, first value. And there you can see column, second row, first value is a 1. So let's go ahead and take the same idea, and we're going to go ahead and I think to clear out the variable explorer, we just restart the console. I don't usually wind up actually clearing that out. I usually wind up closing things out entirely. Anyway, so we'll do the same lab as before. We have a range of currents, and this is exactly the same range. We're going in milliamps from 1 to 10 milliamps. And notice that, remember, Python does not include our ending value, so I'm going to go a little bit higher, one step above for the ending value, to ensure that we have all the way up from 0.001 to 0.01. And it's giving me an error. Oh boy. Oh, because I did not import Numpy. It's not a good tutorial without some sort of an error. There we go. So there's our vector that we want to see. And I have the exact same array of voltage, just like that. And notice that when we're creating that, when I'm creating these are just 1-dimensional arrays. They're both size 10, 10 elements, and they're 1-dimensional arrays because that's all that we really need for this particular example. And again, we've got our Ohm's law, which is just resistance is voltage divided by current. And there we go. We've got our about 1200 for each of these values. I can go ahead and type this out just to show this in the output. These are a range of around 1200, which is pretty much what we expect. And again, we can go ahead and plot this. Now, we're going to use another library to plot this. We can't just type plot like we did before. we're going to use Matplotlib. And generally, if you're using Python for any sort of numerical computing, basically anything in the engineering field, Numpy and Matplotlib are going to be your best friends. You're just going to be typing this stuff all the time. So keep track of it. So we can't just type plot current voltage like we did before. This time we have to type plt.plot current voltage. And again, we'll get current as our x-axis. There we go. Current is our x-axis, voltage is our y-axis. And again, we have to do some extra work if we want to get a title and some nice stuff on the sides and top, but it'll all work correctly in terms of what it's displaying. And the same exact thing, we can go ahead and do current times 1,000 to change our units, nice and simple. Yeah, so that's a good introduction to how you can do exactly the same things in both Matlab and in Numpy. So we're going to do one more, which is how to do some of this stuff in Excel. Now, just to be clear, Excel is a bit different. Whether something is a row or a column, it's going to come down more to convenience. So it's going to be convenient sometimes to do things that'll have longer columns than rows, so you can fit it on exported pages. But you'll figure out what works best. One of the big conveniences with Excel is that you can type some stuff into a bunch of different rows and columns. I'm just typing random numbers here. I can't tab. There we go. Say, for whatever reason, pretend this is actually meaningful data. You can go ahead and select this here and copy it, and then paste it into a Word document, and it's going to give you a table with that data. And so that can be really, really useful. And that means then maybe sometimes you're going to want to go ahead and do something that is 20 or 30 rows long, but only 5 or 6 columns wide, so that it'll fit on a page. So again, figure out what you need. So as some example, the vectors that we've been working with, we had our row vector was 4, 2, and 3, and we had our column vector, which was 5, 1, and 2. And notice that I'm not typing these where one is a row and one is a column. I'm just typing these both as row vectors, because if I want to do a dot product for whatever reason, and again, to be clear, this is another example where I've never used this before, but for completion, I'm showing you how to do it. You can say sum product equals, and I'm going to, oops, not equals. So sum product is my function. There's a whole bunch of Excel functions that are useful, and it's asking for whatever the arrays are that we want to go ahead and get the sum product or the dot product of. And so that's going to be A1 to C1, that's our first vector, followed by A2 to C2, which is our second vector, and there's our 28, just like we had before. Notice that this is just a value. If I click on it, I'm going to get this function, which may not be what I want. If I copy and paste, I might get some weird stuff, right? If I just directly do a Control-C and click somewhere else and Control-V, I'm going to get something funky. Notice that this is no longer indexing for A1, this A by 1, to C by 1. This is now indexing from A by 5, which is empty, it's a 0, to C by 5. And same thing with A by 6 to C by 6. So when you do your copy and paste, you want to be mindful of whether you're doing a direct copy, or excuse me, a direct paste, or you're just pasting values. So again, just be mindful of that anytime you're using formulas in Excel. It's very, very powerful if you use it right, and very, very broken if you use it wrong. Now, there's no built-in cross product. If you really need to use it in Excel, you can write your own just using the definition of a cross product. And if you Google Excel cross product, you'll see people who have done that. At that point, though, I think maybe consider using Python or Matlab anyway, because you're making life difficult for yourself, maybe. But maybe you'll have some case where that becomes useful. Now, note that if you're working on some stuff in Excel and you realize, oh no, I want to swap my columns and rows, I did this in rows, I want columns, whatever, you can actually just copy the stuff you want, just do a copy, and then wherever you want to paste it, when you go to paste, choose this option here, transpose, and that'll transpose it for you. And again, just to show what that was the fourth paste option, should be the fourth paste option. You might have some other ones. It's the one that has these 2 arrows and says transpose when you hover over it. So that's a useful things to use. Now, we showed a whole bunch of stuff that you could do in Python and Matlab. We're not going to go into all of those details for this particular example, because I don't think that most of the things that we did in Python and Matlab are meaningful to approach outside of an example within Excel. they're meaningful to approach more slowly within those other options. Within Excel, let's just jump right into the example. So to get a number of values with the same, excuse me, to get a number of cells with the same value, because this is going to become useful, for example, for our current example, you just type a number and you grab the cell and drag to get the same value. If you don't want the same value, if you want it incrementing, so like we had our 1 to 10 example, you type 1, 2, and then drag down until you get to 10. Easy. If you want, again, you can do the same thing with decimal values. If you want to be counting backwards, I think we had like 10 and then 9. Again, it'll work the same exact way. Count down to 1. So let's go ahead and do that for our current column. And we're going to say this is 0.001, 0.002. So we have our 0.001 increment, and then go all the way down to 0.01. And then for our voltage, I'm just pasting this in because I typed them up before and I don't want to retype them. Let's say that so this is, imagine you go ahead and set this up. Actually, in fact, I want to show this a slightly different way. You know, for example, that you're going to be going in and doing this lab in your class, and you know that you're going to be collecting a bunch of voltages, and you're a smarty pants. You went ahead and planned this ahead. So you know that your value they're going to be looking for is the resistance. And you know that your resistance value is going to be your same voltage divided by current. So your resistance value is your voltage, your B2 divided by your A2. And we can still do that same drag. So this is B2 divided by A2. I'm looking at this output here. B3 divided by A3, B4 divided by A4, and so on. And so then when I go in and enter in my voltages one by one in my lab, or copy and paste because I had them typed up before, everything updates automatically. I have an instant way to verify, am I getting my measurements correct? Are these in a reasonable range? Is my equipment working? What's going on? And as you have probably dealt with when you're working on a lab and a class, sometimes if you don't do your, like the first thing you want to do when you start getting some sort of values is you want to do some quick math, back of the envelope math, just to verify that everything is looking correct. So this will give you that instantly. It's very, very useful. Now, a quick note about these equations, just again, given by example. We talked about the factor of like changing the resistance, changing the current output. But let's say maybe we know we want to change our resistance. Instead of displaying our resistance in kilo ohms, we want to display it in, instead of displaying our resistance in ohms, we want to display it in kilo ohms. So, how did we do this before? We know that we want to change this to around, or we know that these are going to be around 1.2K, because that's just how we're going to talk about it. So we can actually just throw that into our resistance equation. Now notice that when we clicked and dragged, our B2 over A2 became B3 over A3, B4 over A4, and so on. So let's say I want to go ahead and, again, we know that we want to take our resistance and divide it by 1,000 to change the units. So we're going to say 1,000. Well, if I go ahead and say B2 over A2 times 1,000, that's going to get hinky. Oops, not times 1,000. You're going to watch me type all the things wrong. There we go. Divided by 1,000. In fact, let's go ahead and keep this a little bit. Oh, I completely showed this example wrong. We know that we want to go ahead and, it's probably going to be easier this way. We know that we want to go ahead and move this into kilo ohms, which just means multiplying by 0.001. And so we're going to say times D1. There we go. We're just multiplying by that value. And so that gets our first value at C2 in the correct range. But as soon as we go ahead and drag that down, we're going to have a bunch of multiplying by 0 because, well, we're now trying to multiply by D2. And now we're trying to multiply by D3, and so on. It incremented. So we can avoid that by using the dollar operator. Just type that $sign, and that says don't change the 1 when you drag it down. And if we were dragging right, we would just put the $sign before the D to keep it at the first value. We can even put the $sign before the D in this formula. It just doesn't really make a difference if we're not changing the row. And so that gives us exactly what we want. And so then, like down the road, we can say, oh wait, I don't want it in kilo ohms anymore. I just want it back in ohms. There you go. Or I want it in milliohms for whatever reason. you can change stuff up really quickly right on the fly, and it's very fast and easy. Now, we don't have anything like array indexed in here. If you need the third value in your resistance vector, there it is. Again, just make sure that when you're copying and pasting, you copy it by value rather than just copying directly if you're pasting inside of Excel. But if you copy this value and paste it into Word, if you paste it by value, it'll give you exactly what you want. If you paste it directly, it'll actually give you the value in type of a cell, or inside of like a 1-by-1 table, I should say. So it might be a little bit weird. So just, again, be mindful when you paste that you're always using, be mindful of whether you want to actually paste by value, which is often what you want when you're pasting between programs. And again, we can plot stuff. All you do is you highlight your data. Oops, there it is. You click this button here for, you can either click this button here to quickly get to charts, or you can also, in Insert, you can choose which chart you want from this area here. I usually find that the charts that it gives here, it gives you some recommended charts, and usually it'll have one that you want. So for example, we can do the same thing that we did before, and there's our chart. And you can go in and edit the title. You can use these various tools to change what your chart looks like. Because Excel is designed usually for people working in offices rather than doing extensive programming, it's often a lot easier to get the tools that you need, like looking at videos on YouTube or whatever like that, for how to modify these charts to look exactly like you want. And that can be a bit more accessible than making charts in a hurry on Matlab or Python. So this gives you 3 great tools that you can use for doing data analysis in labs in class, or for projects or anything like that, and covers a whole lot of the basic tools you'll need throughout your electrical engineering classes at UCLA. So there you go.